Let's look how to solve this circuit using mesh current method. So in the problem statement, we're told to find our branch currents, which are labeled for us as capital I1, capital I2, and capital I3. So we want to find these three branch currents as our ultimate sort of goal here. And so if we're doing mesh current method, we always start by, well, we can say how many meshes we have. In this case, we have m equals 2 meshes, which means that we're going to need 2 equations to solve for our mesh currents. And of course, we can label our mesh currents up here. So by convention, we're going to label them as going clockwise. But of course, if we want, we could label them as going a different direction. So I'm actually going to use red for our mesh 2 current, just so I can more clearly identify it with some voltage polarities I'm going to add here in a little bit. Okay, so now what we're going to do is do one equation for mesh 1 and a second equation for mesh 2. So let's start with our mesh 1 equation. And so remember, for our mesh current analysis, what we're essentially doing is KVL. So we're going around this loop and we're doing KVL. So if we're doing KVL, of course, we're talking about voltages. So we could define some voltages here and here if we're going around our mesh 1. And so for instance, we could call this V1 and V2. So if we do a KVL around that loop going in a clockwise direction, so from KVL, we would get negative 15 plus V1 plus V2 plus 10. We're back where we started, so we set that equals to 0. So now, of course, when we're doing mesh current analysis, what we're trying to do is to get all of our voltages in terms of our mesh currents. And the way we can do that is we can use Ohm's law. So using Ohm's law, we can get our V1 and our V2, which we just added in blue there, in terms of our mesh currents I1 and I2. So of course there's going to be no change to our minus 15, so that stays the same. But now we see from Ohm's law our V1 is just going to be 5 times I1. And so notice we do need to keep in mind passive sign convention. Because our reference current is going through a reference voltage drop, we're good with just using a positive sign. So now when we go to replace V2, we have to realize that not only is I1 coming through this 10 ohm resistor, but we also have I2 coming through this 10 ohm resistor. So we have to account for both of those mesh currents when we do this term. And because, again, because of passive sign, our I1 is going through a voltage drop, well, let me go ahead and say we're going to have the 10 ohm resistor times both of those currents. Now because the I1 is going through a voltage drop, it has a positive sign. And because our I2 is going through a voltage rise, it's going to have a negative sign, so minus I2. And that way we can account for the contribution from each of those mesh currents. And then finally we have our plus 10, and we set that equal to 0. So if we gather our terms, what we'll end up getting is we have 15I1 minus 10I2 equals 5. And so that's going to be our mesh 1 equation. So now let's move on to our mesh 2, where we're going to do a similar thing to get our mesh 2 equation. So again, we're doing a KVL, so we can define some voltages here. I'm going to put them in red. So let's say we call this voltage here V3, and this voltage V4, and this voltage V5. So notice I've drawn these polarities such that our current I2 is always going through a voltage drop. So if we start in the top left corner and do a KVL, we're going to have V3 plus V4. So let me just say explicitly here we're doing our KVL. So we have V3 plus V4, let me scroll back up here, minus 10 plus V5. So minus 10 plus V5, we're back where we started, so we set that equal to 0. So now same thing, we're going to use Ohm's law to get those voltages in terms of our mesh currents. And so for V3 and V4, that's pretty straightforward because we only have mesh current I2. So that's just going to be 6I2 for V3 and 4I2 for V4. So 6I2 plus 4I2 minus 10, no change there. And now for our V5, we're going to have the 10 ohms times both currents, but again, we are going to have I1 and I2 interacting with this 10 ohm resistor. So let's go ahead and say we have the 10 ohms times, but now that we're looking at this red polarity for V5, I2 is going through a current drop, so it's going to be positive, and I1 is going through a voltage rise, so it will be negative. So we have I2 minus I1, and that's equal to 0. And so if we think about it, this kind of makes sense. So let's take a closer look here. So essentially this term highlighted here corresponds to our V2. And then let's come down here and we can highlight this term in red, which corresponds to our V5. So if we look at the two terms, we can see that they're just the negative of one another. And that makes sense if we come back to our circuit because we see that V2 is equal to negative V5. Okay, so let's collect terms for this second equation as well. So we get negative 10 I1 plus 20 I2 is equal to 10. And so this is going to be our mesh 2 equation. So now we can use any of our solution techniques to solve this, but like I usually say, the matrix method is going to be a little better later on because it's more flexible in terms of what we can do. So if we have our variable matrix, which is what we're solving for, I1 and I2, we set that equal to, and now let's put in our coefficient matrix. So coming back here, we see our first row is going to be from our mesh 1 equation, 15 and negative 10. And this matrix is going to be inverted. From our mesh 2 equation in our coefficient matrix for row 2, we're going to have negative 10 and positive 20. And we're going to multiply that matrix inverted by our constant matrix, which from mesh equation 1 we have 5, and from mesh 2 equation we have 10. So 5 and 10. And so if we evaluate that, what we'll find is that both our mesh 1 and mesh 2 currents are both equal to 1 amp. But we weren't asked to find our mesh currents I1 and I2, we were asked to find our branch currents I1, capital I2, and capital I3. Well, looking at this circuit, we can see that I1, capital I1, is the same as lowercase I1, and capital I2 is the same as lowercase I2, so let's go ahead and write both of those down here. So we have capital I1 is equal to lowercase I1, our mesh current, which is just equal to 1 amp. Okay, and we have I2 is equal to lowercase I2, which is just equal to 1 amp as well. And now we want to find out our branch current I3. So for I3, which is right here, we notice that's going to have a component of I1 in the same direction and I2 opposing it. So there's a couple different ways we can think about that. We can look at the branch and we can say, well, I1 minus I2 is going to be equal to I3. We can just kind of look at the branch and think about it that way. So I1 minus I2. Another way that we can do it is we could consider doing a KCL at either of these two nodes. So for instance, if we're looking at the top node, we could say, well, we have I1, lowercase I1 coming in, lowercase I2 coming out, and out of the bottom here, we have uppercase I3. So let me just label those for clarity, I2 and I3. So we could get that relation from a KCL at either of those nodes highlighted in purple. In either case, we're going to get the same equation, which is the difference of I1 and I2, which is of course 1 minus 1, which is going to give us 0. So that's how we would solve that using mesh current analysis. If you have any questions, please let me know.